Hello there. I am creating this video as another example of the truss analysis. This one is it's a similar example as the last one, but this time I'm not going to use the analogy. I'm not going to say that it's Jacqueline pushing on Lucas, Lucas getting tackled, all that crap. I'm just going to straight up show you the problem, but I am going to keep everything color-coded because I think that helps some people learn, and let me know what your opinion is on that, whether or not the color-codedness helped you. But I'm also going to go through with things again, both the way that Christo would and the way that I prefer, and I'm just going to try to overall do everything in as many ways as possible, so that way one of them ends up working for you. Okay, so what problem am I going to do? I'm going to tackle this one right here in the PowerPoint. So let's see, I can just select all those, copy, and I'm just going to paste that right in here. Okay. We're not going to need that for too long, because we're basically going to redraw the drawing and then get rid of it, but we can put that up there for now. Okay. So, what do we have going on here? Oh, by the way, there's a 4 right there. I don't know why I got cut off, but notice that that's this 4 feet right there. Copy, paste it in here, right? Yeah, that's... there, so 4 feet. So, I mean, we're going to take that out in a little bit anyway, but that's what we have so far, our setup. So, let's draw the main points. There's this one right here, which is just like a pin, right? That's one of our Lucases. So that's just this guy. Again, right here, that's just a pin, as it's called. Over here we have one of the things that's anchored in, kind of like, who was this? This was Jacob Buckman, because he was bad, so he got handcuffed to the lockers. And then we've got, crap. Sorry, I forgot I'm going with the color coding. We've got the block, Buckman, right? We've got, let's see, crap, not enough colors. We've got this, we only had 3 people in our last one, so this is some new character, and then we've got Jacqueline down here, and she was, I think, this bluish color. But remember, she was kind of like Buckman, except that she wasn't anchored to the, or rather, she wasn't handcuffed to the lockers. So likewise, in this example, Buckman is going to be hooked into the ground. I don't know the best way to really demonstrate that, other than maybe saying, okay, he's like bolted into the ground or something, right? So he's attached, Jacqueline's not. So I'm gonna stop using those names and just start using colors. Actually, here, let's do this. Maybe this will help. I'm gonna choose black text. Okay, so new characters. We're gonna make this Alejandro, right? Alex Orsini. We're gonna make this Bar, because he's crazy and he deserves to be in a couple good analogies. We're gonna make this Caroline. So that's Caroline, and this is Dan Tekish, or Dan Herzog, maybe, whoever we want it to be. So now A, B, C, and D, simple enough. I'm going to switch back and forth. I'm using A and B and C and D. The colors, I'm going to use them probably interchangeably: green, pink, yellow, blue. I'm going to try to use them all to make whatever works seem obvious. So now what can we do? How about we draw in where each of these their arms are, or basically what each of them is doing, where each of them is pointing basically where each of these wooden blocks are. And you'll see why I'm only drawing it part way in a minute, because what I'm going to do there is I'm going to basically put whether it's either tension or compression because that does play an important role. In fact, when I was first working towards solving this problem, whoops, nothing there. When I was first learning to solve this problem, I actually neglected to pay attention to the fact that one force was tension and one force was compression, and that ended up giving me a wrong answer, which kind of confused me for a little bit. But hopefully this will not confuse you, because I've made that mistake, so that way you don't have to. Okay, so what's going on here? We've got a 60-pound force. I'm just going to write the numbers, right? Because it doesn't matter if it's pounds or newtons or anything, really. It could be any unit of force. It could be whatever. This is 60, 100. I'm going to draw the arrows in a sec. 80 pounds. This is 4 feet. This is 3 feet. And real quick, that way I can just put it in here while I have the right tool out. What's this diagonal? Well, for one, you can just know that Dr. Truss likes to use 3, 4, 5 triangles a lot, because those are just the triangles he seems to like. So this is 5. I can just tell you that. But if you didn't know that, you would just use the Pythagorean theorem. X squared plus y squared equals z squared. Or rather the square, yeah. So you would square this, you get 9, square this, you get 16, add them together, you get 25, the square root of that is 5. So here we have 5 feet. Let me move each of these to where it kind of best is out of the way, but is clearly visible. These I'm going to draw the vectors for. Okay, so what vectors do we have going on here? Well, we've got this main one, right? That's one applied force. That's another applied force. And this is a third applied force. And this looks like an ugly problem, right? Now there's 4 pieces, there's this diagonal piece, 3 forces going on here, we've got these side lengths. So how do we go about solving this? And first off, let's just review what our sines and cosines are in this case. Right? We said that I'm going to put these in white as well. Our sine, whoops, meant to put that in white. Our sine. Now, we could say that this angle is theta, or rather, let's say that this angle is theta, right? So sine of theta is equal to what? It's the opposite over the hypotenuse, right? SOHCAHTOA. Hopefully you've heard of that. If not, let me know and I'll tell you what it is. SOHCAHTOA, opposite over hypotenuse, that's 4/5. 4/5. And cosine of tangent, or rather cosine of that theta, is adjacent over hypotenuse, which is 3/5. That's 3/5. And using this, we could come up with what the angle is. In fact, if I were to actually want to do that, I could say I would do 4/5 equals 0.8. Then I could go inverse sine. And that tells me that that's a 53-degree angle. And then if I take the 3/5 and take the inverse cosine, we get that, oops, what did I do wrong? 3/5 equals 0.6. If we take the inverse cosine of that, we should be getting, that's weird. No, I'm putting this in wrong, I guess. 3/5 equals, and then we take the inverse sine of that, and that'll work. There we go. There we get that 37-degree angle that Dr. Christo always uses. So what do we have going on here, right? The sine of this 53-degree angle, we found out this is 53, but we don't really need that. We're just going to say that it's 4/5 and 3/5, because that's what he's going to use, and then you're going to want to get used to that. So that shouldn't be too hard to understand, really. Opposite over hypotenuse, adjacent over hypotenuse. This is just the ratios, what they are. We're going to say each of these, well, what's 4/5? Well, hopefully you know that, but if not, 4 over 5, that's just 0.8. 0.8. And likewise, 3/5 is 0.6. So that's what sine and cosine of this angle right here are. This angle is t. So that's equal to 53. Actually, whoops. Why don't I just erase this and use the text tool, since I'm being all neat and fancy and everything. So I take out that text tool. I'm going to put it right here. We're going to say t equals 53. And then this would equal 27, but we're just going to ignore that for now. And, well, that's kind of like all we need. So we're going to begin the problem now. Let me move this down towards the corner over here. That way we can start working on it. Okay, what is the, well, first off, let's figure out all the different relationships that we have to figure out, right? What different relationships are there? Well, we've got A is attached to two different pieces, right? So I'm going to write A twice. A. Okay. And then we've got B is attached to three different things. So I'm going to write B 3 times. B, B, B. D is attached only to B, right? So I'm going to write D once. But wait, actually no, I'm sorry. D is also hooked into the ground, right? Or rather, it's not hooked into the ground, but it's still pressing against the ground. So we still need to figure out how hard it's pressing against the ground, or how hard it's pressing against the floor. So we have 2 D's. So I'm just going to put 2 D's in there. And I'm just putting these in so that way I have all the letters ready to rearrange in a sec. And then C is touching 3 things, right? The ground, the A, and the B, or Alex and bar, or green and pink, however you want to look at it. So C, oops, yellow, C, C, C. So now I'm just going to arrange all the different combinations, right? A is pressing on C, right? A and C are pressing on each other. A and B are pressing on each other, right? Right there, A and B. We've got B and C are pressing on each other. That's a force that's going on. What else do we have? We've got B and D are pressing on each other. So B is active. And then we have one other piece of stuff here. Listen to me. And that's the ground, right? The ground. So each of these is being pushed on by or pulled on. Well, it would only be pushed on by D, right? Because this isn't hooked in. But C could be pulling on the ground. Maybe if somehow something's trying to pull its anchors away. We'll see. So now we have the different forces that we're trying to figure out. And as it turns out, there will also be one more force that I'll get to at the end of this set of videos that I'll get into. But these are the main forces that we're trying to figure out. And then there's going to be one more. But we have all the relevant information that we really need. So in the next video, we're going to start actually solving this truss. So I'll see you then.